Hey everyone. Now when I was thinking of making this video, I wasn't sure how to approach it because there's a lot of different subjects I want to talk about, from SDR receivers, frequency displays, sampling, FFT, Nyquist theory, all sorts of things. So I'm just going to go ahead and talk through all different stuff, and if you learn something, that's great, and if you don't, that doesn't really matter because it costs you fuck all anyway, so it's neither here nor there. So I'm just going to go through some of this stuff and maybe you'll learn something from my ramblings. I'm going to start off with a simple little demonstration though. So here I've got a speaker, but today I'm going to use it as a microphone because when you've got movement here with the coil and magnet, it generates electricity. So that's really all a microphone does anyway. And that's what I've got. And so I'm going to hook that up to the meter here, which I'll show you in a second. It just shows positive and negative over time. That's all it is. So as I push down on the speaker here, you'll see the line went down and then went back to the middle because there's no movement. And as it comes up, it goes up to the top and does movement. So if I just move that at a steady rate, like just pushing it in and out, you can see that's going up and down. Okay, so what that's doing is it's getting the voltage that's being produced by this thing as I move it, so corresponding with my hand or voice or whatever it is that's making this thing move. And as this goes positive and negative between it for the different directions, up and down, it's sampling those. So it just takes a sample of the voltage. So what I can do is I can move this up and down and pause this scope. So what you can see there is it's a little bit above the middle line. The middle line is just 0 volts, so it's neither positive nor negative. But I just froze this display when it was a little bit up from 0. So that's what sampling is. It just takes samples of the voltage at set periods in time. So now I've increased the time period that it's showing here, so you can see a few up and down cycles as I press this. And if I pause that, you can clearly see. So the original waveform is what you can see there. But if you go in really close, which I can't do on this, you imagine that it took a sample there, and then a bit of time went past, it took another sample and it was there, another sample was up here and down there and down there. So that's how it samples analog signals and turns them into digital. Okay, now I'm going to put this SDR receiver into the computer. That one was coming from a different one, but this frequency display on the screen, it doesn't come directly from this. It has to be calculated. So I'll show you what actually does come from this. So this is a very simple little program I've got here just to show you some samples. So this is just to access the device. This is the sample rate. Now that's saying it's going to do 2 million samples a second. So every second it's going to check what's going on 2 million times. The center frequency, that's not too important for this. The main thing is I'm going to read 2 million samples a second. And down here, look, I'm just going to do it a few times first because when you first start this, there's some spurious samples. So that's why I've got it running 20 times here, even though I'm reading just the end value. So I'm just going to read these samples. I'm going to grab 256 of them and then print them to the screen. That's it. So when I run that, you watch what happens. That's it. So these are a whole bunch of samples from that thing. And what you'll notice is they're complex numbers. So you can see the normal number here, then you've got the imaginary one here, the J number. So you've got the real and then the imaginary together, making a complex number. And I just read 256 of them, so there's 256 on the screen. They are a bunch of samples, and that is all this device does. Okay, what I've done now is I've just put the antenna that's on the roof into this SDR receiver and just plug it back into the computer here. So it's got a real antenna on, so I can tune some FM stations and see what's going on. Okay, now I've expanded on that program and I'm going to do a few things. So what I've done here is up to there, the same as before, where I just grabbed some samples. Now I'm running the FFT process on it. Now FFT is fast Fourier transform, and it's a fast implementation of discrete Fourier transform. Now discrete in this sense means discrete intervals of time that the samples were taking. There's lots of discrete samples, so we do discrete Fourier transform on them in a way that's called fast Fourier transform. Now the way that works is, because I've done 256 samples and I'm passing that to the FFT function, it means that there will be 256 frequency bins, they're called. So from the lowest frequency to the highest, there's 256 of them because it's the same as the amount of samples. If I did 1,024 samples, there'd be 1,024 bins. It's always best to have that a power of 2 number because of the way the FFT transform works. So what's going to happen is from the samples that I grab from the receiver, FFT is going to create the frequency bins of the frequency components in there. So it's pretty tricky. Then what I'm going to do is I'm just going to plot it to a graph. But before I run this, I've got to tell you that the output of an FFT function is always going to be complex numbers. In this case, as you saw, I've got complex numbers going in. But even if they were just real numbers, it would still be complex going out, because you can actually go from the output and go back to the time domain. So we're starting off with what we call time domain, like I showed on the little scope there. Over time, the samples, that's the time domain. FFT is going to convert it to the frequency domain, and you can actually go back to the time domain, except I'm going to get rid of some details so we won't be able to go back. But anyway, I'll just run that and show you something. And I'll show you a little issue too. So you see at the background here, it says casting complex values to real discards the imaginary part. So the way I'm graphing this, I'm using the FFT calculated complex value, but I'm just using it for the Y part on the graph here, the Y axis. So it doesn't make sense that I'm trying to put a complex number on here. So what it warned me about was it's just going to discard the imaginary ones. So I'm only using the real ones. So this isn't accurate at the moment. But what I do want to show you is there's positive and negative going on here. So what I'm about to do is get the absolute value of that complex number. So I think I'm going to stop for a second and just quickly go through complex numbers, maybe on the whiteboard, and give you a quick rundown on complex numbers. Right, now I'm going to draw two axes here. One and another one. Now you might know these as different things. You might call this X and this one Y. You might call this one real and this one imaginary. You might call this one in phase, and you might call this one quadrature. Quadrature. You might call this one cos, and this one sine. And what else do you want to call them? But it's the same thing. And now I'm going to teach you complex numbers. You may remember at school or some point in time, I'll just piss that off so I've got the room to do this. You might remember the number line, okay? They said that's 0, and they said that's 1, 2, 3, 4, 5, and so on. And back this way, you got -1, -2, -3, -4, -5, and so on. Now they're called real numbers, but that's one number line. So they made up another number line called imaginary numbers. And it goes up here, 1, 2, 3, 4, 5, but it's 1J or sometimes I or J. So 1I or 1J, 2J, 3J, 4J, 5J. And down here, the negative version. So -1J, -1I, -2J, -3J, -4J, -5, and so on. So that's complex numbers. It's just two different planes, two different number lines. That's simple. I didn't know that at school, but I failed everything at school, got expelled, never went to uni. But that's the number line. So I'll just zoom in a bit here. If you had a point, let's say that's, I don't know, there, you can see it's 3 along this way, plus 2J. And that's similar to how those samples were represented before when I showed you. So one up here would be 2 plus 4J. One down here would be 3 minus 3J. That's all it is. It's a pair of numbers, one on the real line and one on the imaginary line. So that's it for here. Actually, one more thing while I'm here. If you've got a vector that goes, let's say, 3 that way and 4 that way, so that's 3 plus 4J, and I want to get the absolute value of it, that would be the value here. So if you think that went 3 that way and 4 that way, you know that from Pythagoras' theorem that, 3 squared plus 4 squared equals 5 squared, so you know this is going to be 5. So the absolute value of 3 plus 4J is 5. So just keep that in mind, because I'll get to something like that in the computer in a minute. Right, so back here, that output I had here before wasn't absolute values. It was just the real value of the complex number, which is a mess now. So that's not accurate. That's why I didn't want to go too far into what we're seeing here. So now what I'll do is I'll quickly edit that program. You can see where I'm plotting that down here. I'm going to just remark that one out and use this one here where I've added this absolute. So I'm now going to show the absolute value. So now you can see it looks a bit more what you'd expect. And it doesn't go below 0. There's no negative values now because it's an absolute value. Don't worry too much about the scale on the left here, but you can see that it's 2 meg wide down the bottom. So that's 0 to 2 times 10 to the power of 6, so it's 2 meg. There's a bunch of frequencies, and you can see where there's energy there. So far so good. But now I'm going to show you what's running in the background on GQRX. Okay, I'm going to pick a different frequency where 100 is in the middle. So you can see 100 here, just because it's not swamped with stations everywhere. You can see a big strong one here, and one down here, and one up here. So what I'll do in my program is make the center frequency 100 meg as well. So when I run that, that's what I get. And that was the original, well, the live one that you've seen on GQRX. Now, if you look at those, they don't look the same at all. Again, forget the values going vertically, but the strong station here is down here. And you've got another one here, then another one, then not much. And it trails off to nothing up the top here. So what's going on there? Now, this is the hard part to explain. The output of the FFT function there starts off from 0 and it goes in what we call the positive frequencies. So what you've got to do when you look at this display up here on GQRX is just assume that the middle is 0. So when I had that speaker before and it wasn't moving at all, that was 0. And then when I started moving it, that was some sort of frequency, going positive. And that's where it starts. So this 0 down here is the start. And where it hits that first one is where it goes up to this big one here, this Bay FM. Then it comes down a bit, goes to the next one, which will be this little bit here. It's not really much on this. But then what happens is once it gets to half of the sampling rate, it then continues from below. So down here, this Rebel FM Gold Coast will be past 1. So 1 on this, half of the shown output here, is the very left part. So it goes along, so that won't be that. That'll be it there. So almost 0.5 into it. So yep, 99.4. That's almost 0.5, and that's it. And it goes along there, and then there's a whole lot of nothing, which takes you back up to the start. So that's what the output of FFT looks like in its native form. But see, there's also another little thing here called FFT Shift, which shifts that 0 so that it's in the middle, which is the one you're used to. So instead of plotting that, I'm going to plot that. But it's also going to still be numpy.absolute. Another bracket, missed a bracket. Okay, so now I'm doing the absolute, but I'm also shifting it. Okay, so when I run that, it just shifts that 0. So I'll put that back to where we were and put the one in the background up. And you can see it starts to look more like this. Again, the gains are different and all the rest is different, but there's a distinctive strong signal here that you can see correlates to that. So where that's 100, it's actually 100.3. So that's 0.3 round about there. And see how it's got the 0 in the middle now, and it's got positive 1 and negative 1 rather than just 0 to 2. So now I've got to talk about sampling rates. Okay, now this is a bit rough, but all I've got here is a signal being generated at 10 kilohertz, shown on both the time and frequency sinks here. And the sample rate is 44.1 kilohertz, which is the same sample rate as CDs. So when I run this, let's see what happens. So look, the top one's a bit hard to see, it's a bit messy, but that's 10 kilohertz. But down the bottom is the FFT output, and you can see that it peaks at 10 kilohertz. There's also a negative 10, which I'll get to in a minute. But for now, just look at the 10 kilohertz up here. With the sample rate, I've got a variable, so I can change this. Now, as I said, it's 44.1 kilohertz at the moment. And if I increase that, you'll see that the amount I can show is half of what that sample rate is. But it's not really half. It's half in the positive side and half in the negative side, even though we're just looking at the positive side for the moment. So this 10 kilohertz signal is still shown at 10 kilohertz, no matter what the sample rate is above that. But if I bring it back down, there'll be a point that's double that sample. There'll be a rate which is double the signal rate. So if I get that down to 20-ish, thereabouts, okay, there's exactly. So I'm now sampling that at 20 kilohertz when the signal's 10 kilohertz, and you can see it's just on there. If I go any less than that, so any less than double what the original signal is, so I'll go down to, I don't know, 16 kilohertz sample rate, it's showing this up now as 6 kilohertz, but it's not a 6 kilohertz signal, it's 10 kilohertz. So it's being shown incorrectly. That's called an alias. So this is now aliasing. The reason it's doing it is hard for me to really draw or have any fancy graphics. I'll see if I can find something, put a link to something. But basically, the amount of times that I'm sampling it is not enough to catch the full detail of the wave. So the wave is too high. Nyquist theory says you've got to sample at twice the rate to get enough information to reproduce the wave. So that's why when I go less than twice the original signal frequency, it starts looking wrong, okay? Because the real frequency is off the chart here. This -1 down here is because I'm using real numbers. Now, if you remember when a minute ago I drew the axis there and I had real numbers this way and complex numbers that way. Well, this is only basing off samples on the real line. Where complex comes into it, like I showed initially with the output from the RTL receiver, I'll just quickly remind you, it looked like that. So these are complex samples. They have a real value, which is that part there, and a J value, which is the imaginary part, so the different axis if you like. And that is simply, when it mixes the frequency here, like 98 megahertz or whatever, it tunes it in and samples on the real plane, it just samples it, but it also does a 90-degree phase shift of that mixer there and does a sample 90 degrees phase shifted, which is the quadrature sample. So you've got in phase and quadrature, which is IQ. And that's why I've got a complex number here. So back on this one, I only had real numbers. If I change this, instead of having real, which is what this orange is, and I change it to complex and run that, what happens now is there's two signals coming in, okay? That's the in phase and the quadrature, the 90 degrees shifted. And now there's enough information to determine that it is in fact 10 megahertz only. So I'll just quickly go out to the board and show you a couple of formulas, nothing too scary, but just to point out why the complex samples gives you a definitive signal on the positive rather than a mirror image of itself. So I'll just go back to the whiteboard real quick. All right, now this is the formula for FFT. Basically, I won't go too far into it, but this capital X is the frequency output, the little x is the time samples input. And it just goes from, n is the samples, so from 0 samples to however many there are minus 1. K is just which frequency bin, and blah, blah, blah. So this bit here is where the guts of it happens, this Euler's formula. And that expands out to contain some cos and sine values. And if you just simplify that even further, it ends up being basically cos theta plus I sine theta. Now, remember the I that I said is the same as J, so those complex numbers I and J. If you remember that chart I did a few minutes ago, I said that cos is like this axis over here and sine is this one up here. So the I is how many on that axis. But when you're doing real samples only, without the quadrature 90-degree phase shifted ones, you don't have a sine value, which means you don't have a value up there. And the thing about that is, when this formula all works out, if you don't have any quadrature values, any sine values up here, what you end up with is a mirror image. But there's no extra information there, so it's usually just disregarded. So that's why when you see real sampling only without complex sampling, you'll have your 0 point on your frequency display, and whatever signal you have up here, you'll also have a mirror image of down here. But as I said, there's no extra information, so usually they just disregard that and only show you the positive side. But with quadrature sampling, it's what that represents down here is what we call negative frequencies, and they're the frequencies that are lower than the 0 frequency in the middle that you mix it to. Okay, so a lot of you have heard before that you have to sample at twice the maximum frequency because of the Nyquist theory to get all the information. So you might have wondered, if you've used SDR stuff and you set a sample rate to 2 megasamples, why do you get 2 meg of bandwidth? Well, now you know. Don't think of it as the whole 2 meg bandwidth. Think of it instead as 2 halves. So yes, obviously 2 halves is a whole, but half from the center, which is the tuned frequency, up to, well, half the sample rate. So in this case, it's 2 meg sample rate, so that goes up 1 meg. And also the negative frequency, which because of quadrature sampling, you get a complex value input to FFT, which means you actually get a definite signal out here. And as I showed you before, I've done the FFT shift because in its native form, 0 starts off down the left. So I'll show you something similar to that with my little 3D program that I sometimes work on. Okay, so for this demo, I'm going to transmit a signal using the HackRF, and I'm going to receive it using the RTL SDR. So just from there to there, I'm just going to transmit through the real world and receive it over there. Okay, so you can see my little spectrum analyzer here with the signal there at 900 megahertz in the middle. It's still 2 meg bandwidth. So if I go up a little bit here to 900.7, you can see it goes up there, up to the top, then sort of comes back down if I go down here. Okay, that's all good and well. Now, what I'm going to do is I'm going to modify the code so that all the imaginary parts of those complex numbers are 0. And I'll show you what happens on this. All right, so this is a similar version, but I've just made all the imaginary parts of the complex numbers 0. So it's essentially like having real samples. And you can see, as before, if I change the frequency, the left side is an exact mirror of the right side. So there's no extra information, and I can't be sure what frequency that is, if it's that one there or that one there, because it's a mirror image. Okay, so if that was something like audio where you start at 0, that doesn't matter. You just do real samples, piss everything off on the left, and just use your positive values here. But for this sort of thing, you need complex samples, which is why we use them. Okay, what I've done now is I've set it up again, except I'm going to go further than just 1 meg above 900. So if I go up here, it goes up there as you expect. But actually, I'll go slowly. You can see the signal's still within the limits here. But when I get over, it wraps around the other side. So that's an alias because there's no signal down there. It's actually 901, not less than 900. But if I keep going up, you'll see it kind of vanishes. It ends up disappearing. It's gone off. Okay? And if I bring it back, it'll come back up there. And same down the other end. So I'll just whip it down there. Forget the levels. This is all a bit rough. But as I go off the side there, when I reach that limit of half the sample rate, it comes up here. So that's an alias. And you wouldn't be able to tell the difference between that and a frequency that's actually there. So again, if I keep going, it fades off. And the only reason it fades off is because there's filtering in the device that knows its bandwidth, so it filters it. But now I'm going to give you a demonstration of real-world aliasing. And for this one, I'm going to plug the roof antenna onto the HackRF. The reason is the HackRF's got 20 meg of bandwidth, whereas that other thing's only got 2. So I'm going to use the HackRF for this one. Okay, so now I've got 20 meg of bandwidth, and I'll probably be able to actually hear some of this shit. If I click on a radio station, they're there. Right, just mute that crap. So 20 meg of bandwidth. Now if I go up a little bit, just above FM radio is all the aircraft stuff. Okay, so I'll just the last radio station is Triple J here, and it's 107 point whatever it is, 107.7. I'll just tune that out of the way. So now I'm going from above that. I'm going like, what are we going, 109 to 129-ish almost. So the FM radio is now not what I've got tuned in. I'm tuned up here with a center on at about 119 or whatever this is. But if you look up the top here, up at, what's this, 127, see these things here? It looks a lot like radio. And if I listen to that, there's something there. It sounds like radio. It's not aircraft. Now, if I'll just pick that top one there. I scroll back down this lower frequency. That's Triple J playing. So that is a real-world example of aliasing, where I'll mute them. That's a real-world example of aliasing, where signals that are out of the bandwidth here are showing up on it. So that's a higher frequency in the sense that it's further from the 0, which is the middle. So that's the bandwidth, positive and negative. Higher than that is whatever's out to the side here in either direction. That's still going up from 0. So that has been aliased back down to here. So some aircraft someone just transmitted something there. That's what that line was. But you can see that's a problem if you're using this sampling with aliases. So the way to get around that is simple. I have a filter here. So it's a bandpass filter, which means only a certain amount of the RF band it will let pass. And as you can see, it says 118 to 136, which is for aircraft. And if you look really closely, you'll see from 118 to 136, it reduces it by 2 dB, so there is some loss. But anything from 5 to 100, so less than that, or above it, it's dropping by 55 dB. So I'm going to put that in before the hack RF and show you what happens. So you might even see it on the screen while I do this. If I just unplug the antenna, of course we'll lose everything. Put it into the filter, and then put that into the hack RF. And now you can see an aircraft transmitting, but there's no aliases over there to cover it. So that's worked out well. Okay, so that was a real world example of where aliasing can cause problems with receiving the signals you want. So that's fixed by having a filter on the input, and no worries. So look, that was a very unorganized video, if ever there was one, but I just wanted to get some topics at least in your mind. You might have questions. I might do videos on this in the future, but hopefully that'll give you something to think about. So that'll do for now. Until next time, take it easy.